Hello, Mom. This is Kenneth. I'm from ECB section and my roll number is 219780464. Today's my topic is real-time signal generator from Noise Radar. Noise Radar design based on FPGA technology on both digital waveform generation and real-time correlation processing. Introduction. Software-defined radar concept, which supposes realization of all radar units as digital circuits, has been applied to implementation of noise radar, having such attractive features as convertness, absence of range ambiguities, high electromagnetic compatibility, etc. This novel concept requires design and implementation of digital random signal generators and digital correlators in fast integrated circuits such as FPGA. We present the results of our evaluation of the software defined noise radar design and demonstrate the corresponding digital subunit development on the bias of FGPA-based DSP board. In the experiments, we generate noise signals in digital generator implemented in the FPGA, convert it to analog from the transmit it to propagation medium. Noise radar returns are sampled using onboard ADC and feed into digital correlator, also realized inside FPGA along with the sounding signal copy as the reference. The correlator output is processed using algorithms on hosted PC. Design of noise software-defined radar using X6000M FPGA board on from Innovating Integration Inc. has been evaluated. Block diagram of realizing of software radar concept using FPGA, and by seeing this FPGA there is a big single generator and the correlator at the down of the beside the single generator there is a DAC and the radiated signal going out from the DAC and the received signal coming from the ADC. Both the signals collide at the correlator and the range profile is comes. And this diagram is the realization of software radar concept using FPGA. FPGA board instrument description. The X6000M board is a flexible I/O module that integrates the signal processing core based on the Xilinx Vertex 6 FPGA with memory and high-performance PCI Express interface with the host computer. The X6000M board can sustain real-time transfers to the host computers at speeds reached over 2 GBs. It features two simultaneously running 12-bit 1 GSPS A by D channels. The simple clock signal can be taken either from the onboard lower jitter fill or the external input. Multiple onboard boards can be synchronized for sampling using the triggering and external clock features. The board also features four 16-bit 500 MSPS DA channels that can be used as two channels at 1 GSPS update rates. Features Features for the course mixing and interpolation in the DA devices expands the single generation capabilities. to Nyquist shifting and image control. The Xilinx Vertex 6 SX315 FPGA chip together with 4 banks of 1 GB DRAM provides the platform for a very high performance DSP core with over 2000 max. Close integration of analog I/O memory, host interface with the FPGA enables real-time signal processing at very high rates. The functionality of the computing core can be modified using the framework logic tools for the X6 Broad family. This firmware and software development kit implements an interface to each device that connects them to their control and data communication features on the board. Support features such as simply triggering and the data analysis are implemented in the logic to provide precise real-time control over the data acquisition process. The FPGA framework logic tools support development in either VHDL or MATLAB. The MATLAB BSP supports the real-time hardware in the loop development using the graphical block diagram Simulink environment with Xilinx system generator, signal processing, data analysis and unique functions can be added to the X6000M board to suit application specific requirements. Software tools for host development including C++ libraries and drivers for Windows and Linux. The general view of X6000M. This is the general view of FPGA based on board X6000M Innovation Integration Inc. and the FPGA implementation of random waveform generators for digital generation for noise waveform. We used FPGA realization of a linear congruential algorithm which allows real-time generation of pseudo-random sequences samples. The linear multiplicative or congruential algorithm generates a sequence of pseudo-random integers psi exponentials to 0 to m based on the expression xi plus 1 is equals to a xi plus c of mod m, where a is greater than 0, c is greater than equals to 0, and m is greater than 0 are some integer constants. Properties of this sequence at the array determined by the values a, c, and m, but its particular type is given by starting value x0. The sequence of numbers generated by this algorithm is periodic with a period of not more than m. The length of the period is equal to m if and only if the following conditions are satisfied. C and m are coprime. A minus 1 is multiple of P for the all primes P that are dividers of M. A minus 1 is multiple of 4 if the multiple of 4 M is multiple of 4. For 8-bit device, the value of m cannot exceed 28 is equals to 256. Therefore, the maximum length of the sequence is equal to 256. When choosing constant values according to above conditions, a is equals to 150, 173 and c is equals to 163, m is equal to 56. xo is equals to 03 shown. And we can see the graphs of the FPGA Using LCG, we, we were able to perform on both generation of chaotic and pseudo-random sequences of different types. Shows figure 4 shows output of FPGA-based generator producing impulsed waveform with pseudo-random filling obtained via implementation of LCG algorithm 1 with parameters mentioned above. In we seeing the waveforms that the pulsed waveform with LCG pseudo-random filling A and the random PRF LCG filling pulse generator output B. It should be noted that several simple techniques can be employed to improve the LCG in future. For instance, increasing the M value up to 32 and beyond, then use n most significant bits of the result as generator you put where n is the required result width in bits. The generator developed utilizes the aforementioned LCG algorithm not only for generating pseudo-random filling for the pulse, but also for achieving random pulse repetition frequencies (PRF) capability. The two LCG generators work independently in the case. Typically view of generator waveform of this type is shown in figure 4. The waveforms were obtained using VHDL code simulations in Model Sim environment. The result presented here allows us make conclusion about versatility of the method as it allows creating a program a part of FPGA's memory, a set of different algorithms and quickly switch between them with the need of reprograms the entire device for the desired type of signal. Parallel 128 channel time integration correlator implemented in FPGA. Estimation of cross-consolation function of two random signals enables optimal reception of radar returns to coherent radar and is particular in noise radar NR3 and 5 and under assumption of agradosity of stationarity of the transmitted NR signal E of t and NR written E of t, their correlation function may be estimated as follows: R of t is equals to limitation to t V of t u T minus R dt. In many applications, the samples of the coloration function too are needed from multiple delays T simultaneously. For example, in NR receivers, this enables obtaining range profiles showing dependence of radar return level at the related ranges after sampling of n samples of both transmitted reference and received radar return signals. We get their digital copies and to may be substituted with the following expression: Km is equals to n of an minus m dn. The conclusion of this topic is the result on the use of FPGA based devices for the generation of pseudo-random signal for noise radar are presented exfoliating for linear congruential algorithm for time series generating in real time using a FPGA evaluation board has been demonstrated. We also assured that digital scheme for noise signal generation allows controlling spectrum shape of sounding signals and is very attractive for use in modern noise radar. Multi-channel time integrating correlator has been implemented and tested in FPGA Unix FATIC 6 using X6000M board for innovative integrationing. For testing of the designed correlator, we have used both analog noise signals and pseudo-random signals generated in FPGA. After evaluating the cross-correlator function, the data from the FPGA have been transferred to the host PC for processing, display, etc. Analysis of the results has shown that the developed correlator has rather good applications such as homeland security sensors, ground-based SAR radar tomography, radio camera, etc. A new implementation of relay correlator for FPGA has been suggested and tested. That approach suggested enables exclusion of usage of multipliers that saves FPGA resources and hence increases number of parallel channels in digital time. Integrating correlator, which is particular extends the working range of noise radar. Thank you for giving this wonderful opportunity.